talk of the morning session is by Oren Mangubi. The talk is based on joint work with Nishit Vishnoi. Oren has done a lot of interesting work on MCMC methods, metropolized Langevin, Hamiltonian Monte Carlo, and also on random walks. And this talk is going to be about using random walks to obtain faster algorithms for polytope rounding and volume computation. So Oren, please go ahead.
Okay, so thank you. So today I'll be talking about faster polytope rounding, sampling, and volume computation via a sublinear ball walk. So this talk is based on a paper in Fox 2019, which is joint work with Nishit Vishnoi. So I'll start off by talking about the problem setting and motivation. And then I'll talk about some previous approaches to this problem. Then I'll talk about our algorithm. And finally, I'll talk about how we bound the running time of our algorithm. Okay, so we consider the problem where we're given a polytope in R to the n, which is defined by a set of m inequalities. And this polytope, so we assume that this polytope contains a ball of some radius lowercase r, and it's also contained in a ball of some larger radius uppercase r. And so the goal is to find a linear transformation for the polytope, which brings it into isotropic position. So in other words, we want to find a linear transformation which makes the covariance matrix of the polytope to be roughly equal to the identity covariance matrix up to some constant factor. So this problem is also sometimes called rounding, the problem of rounding the polytope. Okay, so why do we care about this problem of rounding the polytope? So one reason is that once we put the polytope into isotropic position, so once we find a linear transformation which makes the polytope have roughly identity covariance matrix, then it actually becomes much easier to generate samples from the uniform distribution on the polytope. So for example, if we want to generate many samples from the polytope, maybe in some Bayesian statistics application where we want to compute some integral or some statistic. So then this can oftentimes be done much faster by first finding a linear transformation which brings the polytope into isotropic position and then generating many samples by running a random walk on the polytope. So another reason we care about this problem of rounding the polytope is that it also makes it much easier to compute the volume of the polytope. So specifically in the setting where the number of inequalities m defining the polytope is greater than or equal to the cube of the dimension. So the previous bottleneck before this work in computing the volume of the polytope is actually this pre-processing step where one rounds the polytope and brings it into isotropic position. So if you can improve the number of operations, the number of arithmetic operations that it takes to round the polytope, then you also improve the number of arithmetic operations that it takes to compute the volume of the polytope. Okay, so there's actually a long line of work on the problem of computing the volume of a polytope. So generally, what one does to compute the polytope volume is that one first generates samples from the uniform distribution on the polytope, and this then allows one to compute the volume of the polytope in polynomial time. So typically these samples are generated by running a Markov chain on the interior of the polytope or on a sequence of polytopes where the last polytope in the sequence is the polytope K whose volume we want to compute. Okay, so in the first column in this table, we have various Markov chains, which appear in recent prior works. And some of these Markov chains imply the best previous bounds before our work for computing a polytope volume in different regimes. So that's the first column. And in the second column of this table, we also have the number of arithmetic operations that these Markov chains require in order to compute the volume of the polytope. So the number of arithmetic operations depends on two things. So first of all, it depends on the number of Markov chain steps that the Markov chain requires to compute the volume of the polytope. So that's this kind of middle column here, right after the equal sign. And it also depends on the number of arithmetic operations that we require to implement each individual step of the relevant Markov chain. So most past work has focused on reducing the number of Markov chain steps required to compute the polytope volume. But in this talk, we're instead going to consider the problem of reducing the number of arithmetic operations that are required to implement each individual step of the Markov chains. So in other words, so in this talk, we're going to reduce the number of operations per step of the Markov chain. And specifically, we would like to reduce the number of operations per step for the ball walk Markov chain so that it is sublinear in the input size of the problem. And in this case, so the input size of the problem is the number of inequalities m times the dimension n. So all previous Markov chains, which can be used to sample from a polytope, require a number of arithmetic operations, which is at least linear in m times n to compute each step of the Markov chain. So we would like to reduce this number of arithmetic operations so that it is instead sublinear in m times n. And we're going to do this for the ball walk Markov chain. Okay, so now I'll talk a bit about our results. So we show that when sampling from a polytope in isotropic position, we can implement the ball walk Markov chain in roughly m operations per Markov chain step on average. So this is sublinear in the input size m times n. And we then show that this result implies a cost of roughly m times n to the fourth times psi squared arithmetic operations to round the polytope. So in other words, to bring the polytope into isotropic position. And it also implies the same number of arithmetic operations to compute the polytope volume. So what is this constant psi squared? So psi is a bound on the KLS constant. So when our original result was published, the best current bound was psi equals n to the 1/4. So that's how our original result was stated. However, since then, the best bound on the KLS constant has been improved to psi equals d to the delta for any delta greater than 0. So with some small modifications to our proof, this then implies improved bounds for our algorithm as well, this improved KLS constant. Okay, so our algorithm improves on the previous best bound for rounding a polytope by a factor of n times this KLS constant psi to the -2. So we get this improvement in the regime where the number of inequalities m is greater than or equal to the dimension n cubed. And since the rounding pre-processing step is currently the bottleneck for volume computation in this regime, we also get an improvement of n times psi to the -2 for the number of arithmetic operations it takes to compute the volume of the polytope. Okay, so here we have a more formal statement of our result. So our algorithm is based on the Ball-Walk Markov chain. So what's the Ball-Walk Markov chain? So the Ball-Walk is a Markov chain on the interior of a polytope, or more generally, the interior of a convex body. So at each point in this Ball-Walk Markov chain, to compute the next point in the Markov chain, the Ball-Walk algorithm first proposes a step which is uniformly distributed on a ball of radius 1 over root n, centered at the current Markov chain point. So if this proposed step satisfies all m inequalities which define the polytope, then the Ball-Walk moves to the proposed step. And if it not, then it proposes a different random step. It stays where it is and it proposes a new random step. So this means that in order to compute each step of the Ball-Walk Markov chain, we have to check all m inequalities which define the polytope. So the question we have is this. So how can we avoid computing all m inequalities at each step of the Ball-Walk Markov chain? So to solve this problem, we introduce a sublinear implementation of the Ball-Walk Markov chain. So the way this implementation works is as follows. So first of all, at this initial point x1 of the Ball-Walk Markov chain, we compute the distance to each face of the polytope. So in other words, we want to compute the distance to each hyperplane which defines a face of a polytope. So we have this distance delta I that we compute to each of these hyperplanes hi defining the face of the polytope. And we then wait roughly delta I times n Ball-Walk steps before checking the distance to the hyperplane hi again. So the main idea is this. So at each step of the Ball-Walk Markov chain, we only compute a very small subset of the distances to each of these hyperplanes because we're waiting delta I times n steps before computing this distance again. So this allows us to implement each step of the Ball-Walk Markov chain in a much smaller number of arithmetic operations than if we had to compute the check every inequality at each step. Okay, so now we need to answer two questions. So the first question is, why does this implementation of the Ball-Walk actually work? So in other words, why does the Ball-Walk not leave the polytope since we're only checking a small subset of the inequalities at each step? So to prove that this implementation of the Ball-Walk doesn't fail with high probability, we can see that each proposed step of the Ball-Walk Markov chain is uniformly distributed on a ball of radius 1 over square root of n. So this implies that at each step, the Ball-Walk travels at most a distance of roughly 1 over n in the direction of any given hyperplane, which defines a face of the polytope. So this is with high probability. So in other words, with very high probability, if we wait roughly delta I times n Ball-Walk steps, where delta I is the distance we computed to each hyperplane hi. So if we wait that many steps before recomputing the distance to that hyperplane, then our Ball-Walk will not leave the polytope for a very long time with high probability. So more specifically, if we want our Ball-Walk to not fail for a very large number of steps t, uppercase T, then we need to wait a long time. Then we need to wait a time of roughly delta I times n log to the -1 of t before recomputing the distance to this hyperplane. Okay, so this shows that our algorithm does not fail with high probability. And it also shows that with high probability, our algorithm will follow the exact same steps as the original ball walk Markov chain for this very long time t. Okay, so far we've shown that our algorithm succeeds in implementing the ball walk, but we still need to show that it implements the ball walk faster than the naive implementation. So we want to show that our algorithm implements, more specifically, we want to show that our algorithm implements the ball walk by a factor of n faster, n arithmetic operations faster than the naive implementation. So to do that, we want to bound the expected waiting time, which is this distance delta I we computed to each hyperplane hi times n. So that's the expected waiting time. And to show that, we need to show that on average, this quantity is greater than or equal to roughly n. And this will, if we can show that, then this will lead to a factor of n improvement in the running time of the ball walk. Okay, so we only know how to bound the expected waiting time when the polytope is in isotropic position. So in order to allow us to round the polytope by sampling only from isotropic polytopes, so isotropic convex bodies, more specifically isotropic convex bodies, which are very close in some sense to being polytopes, so they're intersection of polytopes with a ball. So we consider a sequence of roughly n of these nearly polytope convex bodies. So each convex body in this sequence can be transformed into isotropic position by computing roughly n samples from the previous convex body in the sequence. So this construction allows us to round the polytope by sampling only from isotropic convex bodies. So this is the same. So the same construction also allows us to initialize our Markov chain at roughly a uniform random point inside each of these convex bodies. Okay, so how do we bound the total running time of the algorithm, of our algorithm? So there are roughly n convex bodies inside this sequence, and we generate n independent samples from each of these convex bodies. So that's n squared independent samples in total that we need to generate throughout this rounding procedure. So we also show that the expected cost of each step of the ball walk is roughly equal to the number m of faces of the polytope. So we'll also show that. And we also know that the ball walk Markov chain mixes in number steps, which is roughly n squared times the KLS constant size squared on an isotropic convex body. So this result is due to the recent work by Chen and previously by Li and Vapala and other authors. So so every time this bound on the KLS constant improved, this also implies an improved bound on the running time of the ball walk, the mixing time of the ball walk. So putting these, basically these three facts together, so the fact that we need n squared samples and that each step of the ball walk, so we're going to show that it takes roughly m arithmetic operations to compute, and finally that the ball walk mixes in n squared times psi squared steps. Putting these three facts together, we get that our algorithm takes roughly m times n to the fourth psi squared arithmetic operations in order to bring the polytope into isotropic position. Okay, so we still need to do one more thing. So in order to bound the expected cost of each ball walk step and to show that it only requires m operations to compute, we need to bound the expected waiting time before we have to recompute each, the distance to each hyperplane that defines the polytope. So this distance delta I, and so the expected waiting time is then going to be the expectation of delta I times n. So this is the expected waiting time until we compute the distance to our hyperplane again. But we still need to bound the expectation of this distance delta I. Okay, so how do we do that? So to do that, so how do we bound the expectation of this distance delta I to any given hyperplane defining the polytope? So to do that, we're going to show an anti-concentration lemma for polytopes in isotropic position. So what does this lemma say? So basically, what our lemma says is that if we have a point x that is uniformly distributed inside the polytope, so you sample this point x from the uniform distribution on the polytope, and if the polytope is in isotropic position, then if we look at the distance between this point x and any face of the polytope, or more specifically any hyperplane defining HI defining face of the polytope, then the probability that this distance is less than or equal to some number epsilon is bounded by roughly epsilon. Okay, so what does this mean? So in other words, what this lemma is saying is that if we look at this red strip here, so this red region, consisting of all the points that are a distance at most some number epsilon from any given face of the polytope, then the volume of this red region is a fraction of at most epsilon of the total volume of the polytope. So basically, this is an anti-concentration lemma. It says that the volume of the polytope does not concentrate too much near any of the faces of the polytope. Okay, so why do we care about this lemma? So how does this lemma help us? So since our construction allows us to start the ball walk at a roughly uniform random point, so in other words, from a warm start, and our polytope is in roughly isotropic position at each point in this construction, then if we apply this anti-concentration lemma, it implies that the expected distance to each face of the polytope at every step of the ball walk is roughly equal to something on the order of 1. So in other words, this implies that the expected waiting time until we have to compute each hyperplane again is equal to the expectation of delta I times n. And since the expectation of delta I is roughly 1, then this means that we have to wait roughly n ball walk steps before computing any given hyperplane again. So again, this is an average case bound. Okay, so basically, we've shown that on average, we only need to compute the distance to each hyperplane of the polytope once every n steps of the ball walk. So in other words, this means that we get an improvement of roughly a factor of n on the number of arithmetic operations needed to implement each ball walk step. Okay, so we still, of course, need to show that this anti-concentration lemma holds. So why does it hold? So roughly, since the polytope is in isotropic position, the uniform distribution on the polytope is a log, and the uniform distribution on the polytope is a log concave distribution. And it also has a covariance matrix that is roughly equal to the identity covariance matrix. Right, so we have So the reason that this log concave distribution, which is the uniform distribution on the polytope, has roughly identity covariance matrix is because we've brought the polytope into isotropic position. So we're interested in the distance from any point x, which is sampled at random from the uniform distribution on the polytope, the distance between this point x and any hyperplane. So this hyperplane could be a face of the polytope. So this is what we care about in the application to our algorithm. But more generally, for the purpose of this lemma, it could actually just be, we could be looking at the distance between x and any fixed hyperplane. So it turns out that whenever we project this a log concave distribution onto a lower dimensional subspace, the marginal distribution that we get on this subspace after projecting is also always a log concave distribution. So what we're going to do is we're going to take the uniform distribution on the polytope, and we're going to project this distribution onto the line orthogonal to the given hyperplane. And so the marginal distribution on this orthogonal line will also have to be a log concave distribution. And since the original uniform distribution on the polytope had covariance matrix roughly equal to the identity covariance matrix, this means that the marginal distribution on the line orthogonal to this hyperplane will have variance roughly 1. So now we basically have a one-dimensional log concave distribution, which has variance 1, and this distribution tells us the distance between the point x and the given hyperplane. So now we can basically use this fact to show that with probability at least 1 minus epsilon, the distance from x to the hyperplane is more than epsilon. Okay, so since the time that the work in this talk was published, there has been some other improvements relating to sampling from polytopes and more generally from convex bodies. So one improvement, which I already mentioned, was that the best bound for the KLS constant psi has been improved from d to the 1/4 to d to the delta for any delta greater than 0. And there have also been other improvements to the rounding procedures for the ball walk, which allows one to round a convex body in roughly n cubed times psi squared calls to a membership oracle. So in particular, if one combines this new rounding procedure with our sublinear ball walk algorithms, the one mentioned in this talk, then this allows one to round the polytope in roughly m times n to the 3.5 times psi squared arithmetic operations. And so another recent result in the same paper is that using a different algorithm with fast matrix multiplication, one can actually improve this bound further to m times n to the 3.24 psi squared arithmetic operations. Okay, so so far we've shown how to improve the per step complexity of the ball walk from m times n to m in the context of polytope rounding and volume computation. And this improves on the previous bounds for the polytope, for both polytope rounding and volume computation by a factor of roughly n times psi to the -2 to n times n to the 4 psi squared arithmetic operations. So now I'll talk a bit about future directions. So basically, so far, we've shown how to improve the per step complexity of the ball walk from m times n to just m arithmetic operations. So an improvement, so in other words, this was an improvement by a factor of n in the context of polytope rounding and volume computation. So the first question that we have is, can we get the same factor of n improvement to the per step complexity of the ball walk when the polytope is in well-rounded but not in isotropic position? So why do we care about this question? So one reason is because, so due to recent improvements in rounding procedure, so you can get you can round the polytope in a fewer number of membership oracle calls, but at each step in the rounding procedure, the polytope, so rather than bringing the polytope into isotropic position, you instead only bring it into, at most of these iterations, into well-rounded position, but not into isotropic position. So if we can, so this means that if we can improve, if we can show the same factor of n improvement to the per step complexity of the ball walk that we already showed for polytopes in isotropic position, and if we can extend this improvement to any polytope in well-rounded position, then this would improve the most recent subsequent bounce by a factor of roughly n to the 0.24. So our second question is, can we make further improvements to the per step complexity of the ball walk beyond this factor of n improvement that we've already made? So the conjecture that we have is that the per step complexity of the ball walk is actually logarithmic in m, where m is the number of inequalities defining the polytope. And finally, our last question is, can we improve the per step complexity of other polytope sampling algorithms, which may mix in fewer steps in many settings? So in particular, Riemannian HMC, the hidden round Markov chain, or the Daikin walk.
So let's thank Oren. Are there any questions? We have 5 minutes. We can take quite a few questions if there are. So let's maybe start with the question. So okay, can you explain a little bit about what is the main technical challenge if you want to sample from non-isotropic position? Like what breaks in your current techniques, or what is missing in the current techniques?
Okay, so if you're considering the ball walk on a polytope, but the polytope is not in isotropic position.
Yes. Yes, that's.
Right, so, okay, so how do we prove this anti-concentration lemma? So basically what we do, so first, so if the polytope is in isotropic position, this means that the covariance matrix of the uniform distribution on the polytope is roughly equal to the identity covariance matrix. And then if we project, so we want to know what's the distribution of the distance between this uniform random point x inside the polytope and any hyperplane in the space. So it can be either face of the polytope or any other hyperplane. So if the uniform distribution on the polytope has identity covariance matrix, and then we look at the marginal distribution of this uniform distribution on the polytope on this dotted line. So this dotted line is the line orthogonal to this hyperplane HI. So this will imply that the variance of this marginal distribution is 1. And since the variance is 1, this basically says that the probability that the point x is within epsilon, a distance epsilon of this hyperplane, so this probability cannot be greater than epsilon, and the reason is because this distribution has variance 1 and is a log concave distribution. So if the polytope were not in isotropic position, then we wouldn't know that we wouldn't have be guaranteed that this the variance of this marginal distribution on the line orthogonal to the hyperplane, we wouldn't have a guarantee that this variance is roughly 1.
I see. Thank you for the explanation. So there's another question from the audience. Just 1 second.
Nice talk. I'm wondering, for your last slide, the second conjecture, can you explain the intuition why it's log m kind of the conjecture?
Right. So why is it log of m? So basically, well, so first of all, I'm not sure if this conjecture is true. But the main reason is that, right, it can't really be more than log of m.
What is the reason for that?
So can I answer? Maybe an answer is that you don't expect a uniform random point to be close to too many hyperplanes. I mean, the ones that are close is what you need to check. Probably it's true that if you go to the intersection of log m hyperplanes, that's a very small space.
Right.
Was there anything else you want to add, Oren?
Yeah, so that was basically the reason. But I mean, we don't have, I mean, we don't have any reason to believe that it's true. So
at this point, it's more based on intuition rather than having proof. Okay, sounds good. Okay, so let's thank Oren again. At this point, we have the lunch break, which is on your own, and we will be back here at 2 p.m. for 2 more talks, which will